Welcome back. In today's lecture, Lecture 3, we're going to be mostly reviewing inverse functions and logarithms. So first I'm going to jump into what an inverse function is. So let's get a definition. So let f of x be a function an inverse function, and we usually denote it as f to the -1 here of x. It reverses all the inputs and outputs of f of x, of the original function. So it's just a relationship where you take the old relationship and you switch the domain and you switch the range. That's all an inverse function is. An inverse function doesn't always exist. Many times in this class we will let you know that an inverse for the function exists before you begin working the problem. You may also see the phrase one-to-one. So let me put a note here. A function must be one-to-one in order for the inverse to exist. Now you might be wondering, well, what does one-to-one mean? Let me just draw some examples of graphs to show you what I mean. So let's look at this example. So this is going to be y equals x squared. So I want to look at this graph. If you recall, the graph of x squared is just a parabola. And this one's centered, well, not centered, but the vertex is at 0, 0. So it looks something like this. So to be one-to-one, you must pass the horizontal line test. And I'll abbreviate this HLT from now on. So it's similar to the vertical line test, which you might remember is used to figure out if a relationship is a function. Here, you pass a horizontal line all along the graph, and if it hits it in more than one spot, it fails the horizontal line test, i.e. it's not one-to-one. So let's just draw a horizontal line. You can probably see that there's a problem. This graph fails the horizontal line test. So that means it's not one-to-one. So one-to-one means that for every output that you see, you should not have more than 2 elements in your domain that map to that same output. And then visually, it looks like this, where if you take a horizontal line anywhere along this graph, you should not get an intersection at more than one point. So this would fail. So this just means that y equal x squared does not have an inverse function. However, we can fix that. If I restrict the domain, then I can more or less make it pass the horizontal line test. So let's fix it. So let's fix the problem. So I'm going to say f of x is x squared again. You might be thinking, well, that just didn't work. What are you thinking? Well, I'm also going to put a condition that x has to be at least 0. So now let's look at this graph again. So it's our parabola. It's just I'm only concerned with the right side of the graph. So I'll start here, and I'll just make the right side. And now if you check, it passes the horizontal line test. So this passes the horizontal, I'll use my abbreviation, the HLT. It turns out this does have an inverse, and the inverse function is the square root of x for x at least 0. And we know that that's where this function is defined from the last lecture. You can't plug in a negative value for that function. So this and this turn out to be inverses of one another. If you were to draw these two graphs on top of each other, so first let me draw the square root of x graph. You may recall that it starts here and kind of looks something like this. It increases forever, but it is much slower than the y equals x squared graph. So here's my root x graph. Here I'm going to label this one f of x. And then I'm going to draw this graph on top of the former. So it's going to start here and look like this. This is f inverse of x. And geometrically, I'm trying to point out something. So if you have a graph, so f of x, and it's inverse, then they're actually symmetric about this line right here, the main diagonal y equals x. So I'm going to write that fact down here. F of x and f inverse of x have symmetry about the line y equals x. And that should make sense because all you're doing is you're switching the outputs and the inputs. You're saying, okay, y is now x, x is now y. So that's why it has this nice symmetry around the line y equals x. I'm going to give you one more example too. So let's look at this graph. We're going to look at f of x equals x cubed plus 1. So my directions are going to be find the inverse. First question you should ask yourself with inverse questions is, does this thing even have an inverse? And it will. If you recall, the general shape of an x cubed graph is something like this. I have my y-intercept at 1, so I'll plug in 0, 1. And then they look something like this. That's my cubic graph. And it looks like I've gone off the screen a little bit, so I'll put my arrow there. If you pass a horizontal line along this graph, you only ever intersect at one spot. So this will pass the horizontal line test. This will indeed have an inverse as well. So how do we find the inverse? Let's go ahead and do it algebraically. So often you can actually do it yourself using algebra. Instead of having f of x here, I'm going to rename this y. Next, I'm going to switch. So we're going to interchange all x's and y's. So that's just the algebraic step you do. So once I do that, it's actually x that's equal to y cubed plus 1. And now what you're going to do is you're going to solve for y. So to do that, I'm going to subtract 1 to both sides. And then how do I undo a cube? I take a cube root on both sides. So it looks like this. Cube root equals y right here. And now you can call this the inverse function. So f, let me move that up a little bit. F inverse of x is equal to this. So to check your answer, what you can do is you can place the inverse inside of its original and the original inside the inverse and check that you just get x. So here's what I mean by that. Let's check and make sure my answer is right. If you take f and plug f of x into f inverse, that's f inverse of, my f of x was x cubed plus 1. And if you plug x cubed plus 1 into the answer we found, you get the cube root of, for this x right here, I'm plugging in the original function, plus 1. Well, the plus 1 and the minus 1 under the radical cancel, and a cube root and a cube cancel. So you just get x. So when you plug in x, you simply get x. And I'm going to leave it to you to check the other way. Also check that f of f inverse of x is equal to x. And it is, but you can check that on your own to make sure you understand. So you'll plug in now the answer you got into the original and make sure you get it equal to x. OK, from here, we're going to do more examples of finding the inverse. And then after that, I think we'll start talking about logarithms as well. So I'll see you soon. OK, so here's another example. We're going to explicitly find the inverse of f of x equals x minus 2 over x plus 3. What type of function is this? Remember from last time that this is called a rational function. I have a polynomial divided by a polynomial. All right, let's try to find the inverse. The directions tell you to find it, so you can kind of assume it exists in this case. Again, a lot of the time we'll just tell you find it. We won't tell you to prove that there is one. OK, so what I'm going to do first is I'm going to interchange my x and my y. So that's going to become x equals. I shouldn't keep going. I should tell you to pause the video and try it on your own, right? That's what a good teacher would do. If you feel confident, don't sit here and just autopilot and watch me do it. Pause your video for a second and then try it and then come back, OK? Promise? OK, I'm going to do it now. So x equals y minus 2 over y plus 3. So in this instance, we had two different spots that needed to be switched with y, and only one spot where a y needed to become an x. OK? We're going to clear the denominator by multiplying both sides by y plus 3, just like this. Notice that this will cancel this. That's why I did it. And here I'm going to go ahead and distribute in the x. So I'll get xy plus 3x equals y minus 2. Now remember, the goal is to solve for y again. So solve for y. To do that, I should get all my y's on one side. So let's move this y to the left side. And we'll get xy minus y equals negative 3x minus 2. So I've moved the non-y term to the right side. Do you remember what you can do here now? They both have a y, so we're going to factor. So y times x minus 1 equals negative x minus 2. And then the very last step to solve for y is you're going to divide by this x minus 1. So you're going to get negative 3x minus 2 over x minus 1. And we just have to hope that x is not equal to 1, right? You just don't want to divide by 0. And then this I'm going to label as my inverse function. So this equals f of x inverse. OK, so that's how you find the inverse of this function. You could do the same check we did earlier where you plug this into the spots here and see that it reduces to x and then vice versa. I won't. It takes a little longer than the last example. However, let's talk about the domain and range of what we just did here. So let's look at f of x. Let's look at f inverse of x. And we'll look at the domain and range. So I'm building like a little 2x2 table. That's what I'm doing here. And let's talk about what the domain and range are for these. So some of these are not easy to get right away, but I'm about to show you a trick to get all of them. So let's go to the original function. What is the domain of the original function? There's one number you're not allowed to plug in, right? X cannot be negative 3. OK. Another one that's pretty easy for us to get is to look at our answer for the inverse, right? What's the domain of the inverse? I actually kind of wrote it here, didn't I? The domain of the inverse function is everything except x can't be 1. Okay. Now, because the inverse and the original function just switched their x and y coordinates, all that's going to happen is that the domain and the range are going to switch. So the domain of f of x is going to be the range of f inverse of x, because we're switching all the x and the y coordinates. So this one is going to be y is not equal to -3. Remember, we're talking about the range, so we're talking about specifically just y here. And then if the domain of the inverse is not 1, the range of the original, y is not 1. And now we have the domain and range of both of them. So the domain is easier to find in this case than the range, so that's why I found these two first. And then that was enough information to complete my table. So I hope that made sense. That's another good thing of working with an original function and its inverse, is you can quickly get the domains and ranges. All right, this is going to kind of stop talking about inverses for a little bit. I'm going to shift into logarithms. And actually, I mean, logarithms, they're an inverse of another function, so it's all related. So let me define what the logarithm is. So we're going to let a not equal to 1 be a positive real number. Let me step over here maybe so you can see as I'm writing. And then we're going to recall y equals a to the x looks like what? Do you remember what the exponential graph looks like from our lecture 2? Well, here's my x-axis, here's my y. If you plug in 0, any real number to the 0 besides 0, the technicalities here, but I'm just going to ignore the case where it's 0. It's going to be 1. And let's give my function actual a value, just to avoid this situation here. So we're going to say 2 to the x. If you plug in 0, you get 1. If you plug in 1, for example, you get 2. And then this is always going to be larger than 0 for x a real number. So the graph looks like this at j. So hopefully you remembered that from last time. This graph, you should notice it's increasing, right? It also passes the HLT. It passes the horizontal line test. In fact, it has an inverse. So if you see, if I draw all these horizontal lines, it's fine. It only intersects in one spot. So it's going to have an inverse. So we give that inverse a special name. It's actually the logarithm. So let me write that over here to summarize. F of x equals a has an inverse. We call it the logarithm. It's going to be, that inverse word is going a little too high. Let me lower that. Has an inverse y equals log base a of x. So it has a special name. It's the logarithm. Let's look at the domain and range chart for this. So we'll put D for domain, R for the range, y equals ax here, and then y equals log base a of x here. Let's see if we can fill these out. OK, let's look at the exponential graph. If you look over here, you can see that it's OK if I plug in any number I want, right? For 2 to the x, any real number works. Nothing breaks. So the domain here is all real numbers. That automatically gives us that the range of log is all real numbers. Remember, they just switch because they're inverses. Now we just need one of these two and we'd be done. Well, I guess I could cheat and look at my picture here. So the range is all the y values that you see pictured here. Well, it doesn't ever quite get to 0, but it has every number greater than 0. This is going to grow forever. So the range of the exponential is bigger than 0. Well, then that means that the domain of log must be greater than 0. In fact, you could, if you have a calculator handy, you can try plugging in 0 or a negative number into log, and you'll see that it'll be undefined. So this is kind of our domain chart for exponential, domain and range chart for exponential and logarithm. If I draw the logarithm, you'll have to believe me, but the logarithm actually looks like this. And then you'll have that nice symmetry, just like with every other function in its inverse. So an exponential graph has the point 0, 1. A logarithm, that important point switches to 1, 0. All of the x and y switch. So this right here is log base 2 of x. That's what I drew. So it has that nice symmetry over here. So now what can I do from here? Well, I can give you some important properties of logarithms that you should be familiar with. So let's go over those. Let's go over ln of x, because you're going to be seeing that quite a bit. So ln of x, it's the logarithm with base e. And e is about 2.72. So over here, the log base was 2 because it's based on the exponential graph 2 to the x. So our base is 2 here. ln of x, it's not written, but there's a base e here. The other special one you should be aware of is that log x has base 10. And again, it's not written here, but you would understand that it comes from the exponential 10 to the x. But there is an implied 10 right here. All right, and these are the log properties that I would encourage you to memorize. There are 3 important ones. So the first one is that log base a of any product is the sum of the logs. So log base a of x plus log base a, I almost wrote b, a of y. So you keep the same base, and you can split the multiplication into 2 logs like that. There's also a similar one for subtraction. So we're going to have log base a of x divided by y. This is log base a of x minus log base a of y. And then the third one that you should know is that log base a of x to the y, you can take an exponent here that's with the argument, and you can bring it in front. So this is equal to y log base a of x. And because it's an equality here, you can also take things that are expanded like this and condense it back into the left side as well, if you need to do that. It just depends on what you're doing. Okay, so next time we're going to look at some problems involving these log properties. All right, so on the board, I have 2 log equations, and I've left the properties from just before right here, just in case you need to remember any of these as you're solving these. You can probably guess what I'm about to tell you. I would encourage you to try pausing the video and attempting both of these on your own and see if everything checks out from your high school understanding. So give it a shot and then come back. I'm going to do them now. All right, so this first one, we're going to solve ln of 3 minus 2x is equal to 2 ln of 1 minus x. So I should be on the lookout for any properties that I could use. And I see a 2 in front of log. So if you go to the third property, we could use that. We could take the 2 that's in front and bring it up top. So I'm going to get ln of 1 minus x squared now because I'm bringing it up top. And I'm just going to leave the left side alone. Notice that we don't have a rule that breaks it apart when it's a subtraction. The only reason you can break it up is if it's multiplication or division. So don't let that trip you up. You can't break this up. Okay, I have log of something equals log of something. So one log equals the other one. The only way for that to happen, and this is because log is 1 to 1, is that the two things on the inside must be the same. So what I'm going to do is I'm going to set 3 minus 2x equal to 1 minus x squared. And we're going to solve this. This turns into kind of like an algebra 2 problem. So this will be 3 minus 2x equals. I'm going to FOIL this by doing 1 minus x times 1 minus x. So this will give me 1 minus. Here I get minus x, and I get another minus x to give me minus 2x. X times x is x squared. Okay, with a quadratic, how do you solve this? You set it equal to 0. So I'm going to move these two terms over here. I'm going to get x squared. It looks like minus 2x and minus 2x are in common. So when that happens, you can just get rid of it. Let's move the 3 over. I get minus 2 equals 0. To solve this, I'm going to go ahead and add 2 to both sides. And I'm going to take the square root. So remember, when you take the square root, I covered this, I think, in lecture 1. When you take the square root, you need to include a plus or minus symbol here. There's two possible solutions. What we need to do from here is we need to check and make sure that both of these answers are valid. So it turns out one of them is actually not a solution at all. It's called an extraneous solution. So what we're checking here is has to do with ln's domain. So recall the domain of ln of x, of any logarithm, is, and what was it? It is x has to be at least 0. So what you're doing is you're going to plug in your possible answers into the original, and you need to make sure that whatever is inside the log here does not go negative or to 0. If it does, you have to throw out the possible solution. So let's check. The first thing I'm going to check is radical 2. So this is x equals radical 2. So we're going to go to the very beginning. I'm going to plug it in. So ln of 3 minus 2 root 2. And I also have on the right side, so this is my left-hand side. My right-hand side is going to be 2 ln of 1 minus root 2. Okay, I immediately see a problem here. So it would be helpful to know, and I'll put it over here, that root 2 is about 1.4. So right here on the right-hand side, I have 1 minus something that's about 1.4. This is undefined. So this right here, this root 2 equals x, that's an extraneous solution. So we're going to say it's extraneous. It means it's not part of our solution set. If you plug in negative root 2, everything's actually OK. So I'll just write that down. Negative root 2, x equal to negative root 2, is a valid solution. You can check that right now if you want, but all you would do is take this negative root 2 and plug it into the two spots, and you'll see both sides are equal, and the stuff inside of the logarithm stays positive. Okay, hopefully you got to this one as well, so let's do this example together. So here I have addition of two logs with the same base. That would mean that you'd want to use property 1. Let me crouch down here. Property 1 says that if you're adding two logs together, you can put them together by multiplication. So if I put these two together, I'm going to get log of x times x minus 2 equals log of x plus 10. So you've taken these two, condensed them. Now we're back to the situation before. Log of one thing equals a log of another. So in order for those two sides to be equal, what you're taking the log of has to be equal. So that means x minus 2 has to equal x plus 10. Okay, and we have another quadratic to solve. So what I'm going to do here is distribute. I get x squared minus 2x equals x plus 10. I'm going to set it equal to 0 by moving these both to the left side. So I'll get x squared minus 3x minus 10 is 0. This gives rise to two possibilities. So if you factor this, our factoring is 5 and 2. If you're not sure how I did that, you should review some algebra stuff. But all I did is I found two numbers. They have to multiply to negative 10, and they have to add to negative 3. So they add to the middle one, they multiply to the last one. So that's what I did. These two, you can set them equal to 0, and you'll see that x is 5 and x is negative 2. Maybe. Remember, for these logs, you have to check and make sure nothing goes wrong. So I'm going to check. First, I'll check my 5 and see what happens. We're going to check x equals 5. Go back to the very original. So that's here. Here we have log 5 plus log 3 equals log 15. That's correct. That's perfectly fine. You combine these together to get 15. All of these are positive numbers, so we can take the log of them. You're probably going to guess that this is extraneous. Negative 2, sorry. Our possible solutions were 5 and negative 2 right here. So if you try plugging in negative 2, you'll immediately see right away in the first one that you get log of negative 2 plus, and it doesn't even matter from there. This is undefined. You cannot take the log of 0 or a negative number. So immediately you would throw this out because you see, oh, that's not even an object I can work with. So this is my only solution for this one. Okay, from here, we're going to look at some special inverse functions. We're going to look at inverse sine and inverse tangent. And then I think that'll wrap things up. So I'll see you then. Okay, so last we're going to look at some inverse trig functions. I'm actually going to go over inverse sine and inverse tangent because they are probably the two most important ones. But all 6 trig functions do have an inverse function like partner as well. So let's just review what sine of x looks like. So sine of x starts at 0. At pi over 2, based on your unit circle studies, it goes up to 1. Then at pi, it goes back down to 0. It goes like this. Here it goes down to negative 1. It kind of goes on forever like that. So this is what sine of x looks like. The problem is it doesn't have an inverse function as it is because you could take any horizontal line, like right through the middle, for example, and you hit infinitely many spots. So right now, this fails the horizontal line test. So it doesn't have an inverse because it has to at least pass that. So what we do is we're actually just going to take a little piece of this graph, just like I did with the x squared graph, and then it'll pass the horizontal line test. So what I'm going to do is I'm going to restrict. I'm going to restrict the x so that it's between negative pi over 2 and pi over 2, just like that. And then I'll redraw the graph where I want to give myself a little more room. Let me move this over here a bit. So this will be the sine of x restricted. So sine of x, it's going to go from negative pi over 2 to pi over 2. It starts at 0 here, it goes up, and it goes down. So it just kind of has this one piece that is strictly increasing from left to right, right? So this is sine of x where you have the restriction. And now let's look at what an inverse function might look like by using our table we were using before. So I'll denote the domain as D, the range is R. This will be sine of x, and then this will be sine inverse of x. So this is not the same thing as 1 over sine. This is the inverse function. Now this sine of x right here is our restricted version. Okay, so keep that in mind. So if you look at the domain of what I restricted sine of x to, its domain is negative pi over 2 to pi over 2. That automatically gives us what for the inverse function? You should have said the range. So we automatically know that the range of the inverse will be negative pi over 2 to pi over 2. Now I just need to get one of these, because once I have one of them, the other one is the same thing. And I'm going to just look at my picture of sine of x. So sine of x goes between what two y values? Well, the lowest point is negative 1, and the highest point is 1. So sine of x and cosine of x go between negative 1 and 1. So here for the range, y is between negative 1 and 1, and that's going to be the domain of the inverse function. So x is going to be between negative 1 and 1. And now finally I'm going to go ahead and draw what the inverse function looks like next to the original graph. So the domain goes from negative 1 to 1 instead of negative pi over 2 to pi over 2. And its range goes from pi over 2 here, negative pi over 2, up to pi over 2. And it looks something like this. So I have a point here and a point here. So this point right here corresponds to negative 1, negative pi over 2. So that's the inverse point. That's because on the original, sine of negative pi over 2 is negative 1. So all the points just switch. If you were to line this up on top of this graph, you'd have that nice symmetry that I was talking about earlier. So that's what the sine inverse looks like. Tangent, you build it the exact same way. So I'm just going to go through it, maybe with a little less detail this time. This is what your tangent graph normally looks like. So it's a bunch of these boys right here. Tangent of x is undefined at pi over 2, at negative pi over 2. So you have these asymptotes. You would know this from those unit circle measures we did last time. We would like for this to be 1-to-1, or to pass the horizontal line test. So this one, I need some separation here. This is kind of, maybe it's bothering someone else out there. There we go. I kind of just want a barrier here, so I'm going to put that there. This doesn't pass the horizontal line test, so it does not pass the horizontal line test. The way we're going to fix that is we're going to restrict it to the same domain that this one does. So get rid of these two, and we're just going to leave us with the one piece here. And then we're not going to have a problem when we pass a horizontal line. So we're going to restrict to the same domain as earlier, negative pi over 2 to pi over 2. And then what you're left with is its restriction that looks like this. It's just that one piece in the middle. Here's the point at 0, 0, and here's the asymptote at pi over 2, and the other one at negative pi over 2. So that's the tangent piece we're going to consider. And then what happens with tangent inverse is it looks something like this. So your asymptotes were x values at negative pi over 2 and pi over 2. They become y values when you switch them over to the range. So now we have asymptotes at negative pi over 2 and pi over 2. So these switch to the y. And then this will also flip. So 0, 0 stays at 0, 0 because you switch the x and the y. But the graph looks like this. So we go from negative infinity all the way to positive infinity. We can plug in any value we want. Basically, we've taken this graph and just turned it on its side for the most part. And if we wanted to, we could look at the domain and range of this one as well if we wanted to build up the thing. So let's do that over here. So domain range. Here's the restricted tangent graph. And here's tangent inverse. So the domain of tangent, what I've restricted it to, is right here. It's negative pi over 2 to pi over 2. This immediately becomes the range for this. So this is going to be negative pi over 2, pi over 2. I suppose when I was restricting my range earlier, or my domain earlier, I should not have included the negative pi over 2 and the pi over 2. In the original graph, they're asymptotes. So one slight modification I'm going to make, and you should probably make this in your notes, my restriction is going to be here. So I'm not going to include the pi over 2 or negative pi over 2 because those are asymptotes anyway. So I shouldn't include those. So then over here, I'm just going to make sure I don't include the asymptotes. Sorry about that. So they were included over here because it's actually defined at pi over 2. But here you're not even defined at pi over 2, so I shouldn't be including them. So just a minor thing, but it bugs me, so I wanted to fix it. The range of tangent restricted, it's all real numbers. This thing increases and decreases forever. So this is going to be all real numbers. So that means that the domain of tangent inverse is all real numbers. And that's what we see. We see that you can plug in any number you want left to right, and it's fine. So here's the chart for tangent inverse. Now, I'd like to do one problem where I work with an inverse function. So let's do that right up here. I hope I can fit this here. So here's my example. We're going to find the exact value of, and it's going to be cosine of tangent inverse of -1. So I'm going to show you how that works. I'm going to get a different color and kind of section this off so I don't confuse myself. So let's try this green color, and let's just give myself that space and hope that's enough. And we're going to use this marker right here. All right, so first thing I like to do is I like to call my inverse function in here theta, because the inverse of something is actually the angle it came from. So I'm going to say let theta be tangent inverse of -1. So if I replace that, that's cosine of theta for this. Now, to undo tangent inverse, we take its inverse function, which is tangent. So we're going to apply tangent to both sides. So we're going to take tangent of the left side, and if you take tangent of the right side like this, the tangent and the inverse tangent cancel, and you get -1. So from this piece of information, I know tangent of theta is -1, or -1 over 1. That's the same thing. This allows you to draw a right triangle of the situation going on. So it would be helpful to know what quadrant I'm in. So give me a second to erase this and consider that. Tangent is negative in 2 quadrants, right? Let's do some scratch work down here. Which 2 quadrants is tangent negative in? It's the 2 quadrants where the sine and cosine are different signs. So here in quadrant 2 and in quadrant 4, tangent of theta is negative. I'd like to pick the correct one that I'm in. So here I have tangent is -1. I'm dealing with tangent inverse. So the domain of tangent inverse, if you look over here, or I'm sorry, the range of tangent inverse, if you look over here, it's between -pi over 2 and pi over 2. So that's these 2 quadrants right here. Here's pi over 2, here's -pi over 2. So tangent inverse gives you values that are either in quadrant 1 or quadrant 4. However, it can't be in quadrant 1 because it's a negative number. So that means that we know we're in quadrant 4. So I'm going to write that somewhere for us to use later. So we are in quadrant 4. OK, let's go ahead and draw some kind of triangle here. Okay, here's my theta. Tangent is equal to opposite over adjacent. That was something from lecture 2, I think. So the opposite is going to be 1. The adjacent is going to be 1. I'm in quadrant 4, so this is negative. If I use Pythagorean theorem, this will be the square root of 2 right here to complete the hypotenuse. Okay, so this is the situation I have based on this. Now I can write the final answer. What is cosine of theta? Now that I have all of the sides filled out, well, it's adjacent, which is, so I'll write that. It's adjacent over hypotenuse. That's what cosine is. Adjacent is 1. Hypotenuse is root 2. And the last thing you should always do before you finish problems like this is check the sign. So we are in quadrant 4. Based on what we talked about in the last video, is cosine going to be positive or negative in quadrant 4? Well, this is the x value. So if you look at the x value on the right side, in quadrant 4, x is positive. So this should be positive. If it wasn't, you would just make it negative. Okay, so that concludes that example. We covered a lot in this video: inverse trig functions and logarithms and regular inverse functions. I will see you in the final review video, lecture review video 4. Thanks for watching.